All right, 7, 8, and 9, we're back to hypothesis tests. When we're doing the hypothesis test for the correlation coefficient and the slope of least squares, we're going to do a t-test. And in order to compute the value of t, which we'll get down here for our test statistic, but the value of our test statistic t is going to be equal to r times the square root of n minus 2 over 1 minus r squared. We'll get into all those, but there's the main formula we're going to use. First of all, we have to figure out our null hypothesis and our alternative hypothesis. Newburgh Park, Florida is a popular beach resort town. Property values are fairly high there and, as such, are rather well studied. One topic of study has been the relationship between housing prices and the distance from the beach. For a recent sample of 22 houses, and it's going to be 22 then, sold in Newburgh Park in the past year, the value of the sample correlation coefficient R, relating the variable house price and the distance from the beach, was negative 0.44. So they tell us R is negative 0.44. Test a significant linear relationship between the two variables by doing a hypothesis test regarding the population correlation coefficient P, assuming that the two variables have a bivariate normal distribution. Use a 10% level of significance and perform a two-tailed test. If we are doing a two-tailed test, remember from our previous hypothesis testing, we're testing not equals, right? The one-tailed test had the greater than and the less than. Two-tailed test is a not equals. Therefore, our null hypothesis is P equals 0. And my alternative hypothesis is going to be P does not equal 0. So in this case, those values are always going to equal 0 that we're comparing it to, because we're looking at a line, and if the slope of the line was 0, it'd be that straight across line. It wouldn't have a positive slope or a negative slope. So these values here are always going to be 0. Test statistic, we already said earlier when we do this test, we're going to do the t-test, and then we're going to compute the value of our t-statistic by using this formula. So t is going to equal negative 0.44 times the square root of n, which is 22, 22 minus 2 over 1 minus a negative 0.44 squared. If I smush that all in there. So make sure here, since this is negative, you've got that parentheses around your negative. And we're going to go ahead and punch that in on the Alex calculator, or you probably could do it on your regular calculator since there's no t subs and x subs and all of that yet. And so if you get that number there, hopefully you've got that punched in and checked out. 3 decimal places, you should come up with negative 2.191. Negative 2.191. So, we are going to do our p-value. So since we're doing our p-value, and it's a two-tailed test, remember we're testing greater, we're testing just this side, but we're also going to have the same value on this side since it's a two-tailed test. So I am going to do P of t is greater than our test statistic, which I have to fix on my test statistic because notice this was negative. That means this is the negative 2.9 or 191. This number here would be positive 2.191. So I have to be careful there. If it's a negative, we really want to do the positive if we're testing to the right. Otherwise, you could test to the left and do 1 minus. So, 2 ways you could calculate your p-value. Either you could do 1 minus the P of t is greater than negative 2.191, or just do P of t is greater than the positive 2.191. Those two calculations, if you try them out, should give you the exact same number. Go ahead, test that out. It should give you the same value because either you're calculating the percent to the left of this point or the percent to the right of that point. And it should be the same percentage. Hopefully, you come up with 0.020. 0.020. Those both should be the same number. Again, since this is a two-tailed test, we either are going to just add those together or multiply by 2 to find the total of the p-value. We have 2% here and 2% here, which means we're going to have 4% altogether. So keep in mind here on that two-tailed test, if you get the negative number, it's this number. If it's a positive number, this number. We're calculating our p-value to the right. So if you have the positive number, you just have that. If you have the negative, you've got to do 1 minus. All right, so a couple ways you could get that number. Now I'm going to compare my p-value to my level of significance. Is 4% greater than or less than 10%? Well, we know that 4% is less than 10%. Now we got to go back to thinking about all those other hypothesis testing we did. When the p-value is less than, if the p-value is less than, do we reject or do we accept the null value? If it's a less than, we're going to reject the null. If it's a greater than, we accept the null. Right? This is our percent of confidence. If I only have 4% confidence and I want to have 10% confidence, I didn't meet that level. 4% is less than 10%. So, we're going to reject the null. This is the not true statement. This is the true statement then. If I reject the null is not true. So it says, based on the information, can we conclude using that 10% level of significance, is there a significant linear relationship between house prices and distances from the beach in New York Park? Can we conclude that there is a significant linear relationship? Well, how we're going to figure that out, and this is probably a little easier than the other hypothesis testing, is if this is true, there is no linear relationship. If the alternative is true, then there is a linear relationship. So can we conclude there is a linear relationship? Yes, because the alternative statement is true, we can conclude that, yes. So a little easier to think about than when we had to test all those numbers and then we had greater thans and less thans. It's either if the null is true, there's no linear relationship, and if the alternative is true, then there is a linear relationship. Number 8 then. In an ongoing economics analysis, the U.S. federal government compares per capita incomes not only among different states, but also for the same state at different times. For the 50 states, the least square regression equation relating the 1,980 per capita income, or the 1980 per capita income and the 1999 per capita income is y hat equals 7.97 plus 1.97x, with x denoting the 1980 per capita income and y denoting the 1999 per capita income. The standard error slope of this least regression line is approximately 1.10. Based on this information, test a significant linear relationship between the variables x and y by doing a hypothesis test regarding the population slope B1. Assume that the variable y follows the normal distribution for each value of x and that the other regression assumptions are satisfied. Use a 0.5 level of significance and perform a two-tailed test. So, number 8 here, we are going to do B1. It tells us right here. If we're doing a two-tailed test, it's either an equal or a not equal, which means our null hypothesis is B sub 1 equals 0, and our alternative hypothesis, B sub 1 does not equal 0. Again, we're going to do a t-test, and whenever we do the t-test, we have to have the degree of freedom. I don't know if I wrote it on there last time, and I'm not sure if you have to put it in the drop-down or not, can't remember, but if you do, you can calculate the degree of freedom. We are going to find the degree of freedom by doing n minus 1, or n minus 2 is our degree of freedom. How many states did we look at? Well, we had 50 states. So we know that n is equal to 50, so our degree of freedom is 50 minus 2, which is 48. So just in case you need to put that in there, we'll calculate that right away. You need it anyway later on. So, now we are going to have a different formula because now we're doing a B1 instead of doing the one we did on number 7. So watch, we have different things. Instead of the P, we got B1. To find T, we're going to use B1, which is the slope of our linear regression equation, over SE sub B1. So, the SE sub B1 is that value that they give you for the standard error of the slope. SEB1. That's the number you're going to use for that value. The slope of my linear regression line is this number right here, right? The number in front of our x is our slope. That's going to be the number we use for just plain B1. So when we're calculating t, we're going to use 1.97 divided by 1.10. No big crazy formula, you just need to pick those two numbers out of there. If you go ahead and divide those numbers out, we get 1.791. 1.791. Again, we're thinking about we're doing a two-tailed test here, and we're going to do the critical value. If we're going to do the critical value and we're doing the two-tailed test, we end up having to divide that by 2. So 0.05 divided by 2 would give me 0.025. And that's the value we're going to do for the critical value. So again, when we do critical value, since we're doing the t-test, we do t sub that number. T sub 0.025. If it's a one-tailed test, we use the number given. If it's a two-tailed test, we have to divide that number by 2. Again, we need the degree of freedom. The degree of freedom is going to be 48. So on the LX calculator, you're going to go ahead and do T sub 0.025 with a degree of freedom of 48. When you put that into the LX calculator, you get a value of 2.011. It's a positive number, so we know that's the number on the right. It actually is this number right here, 2.011. It's not the number inside because it's not the percent. It's our critical value for our test point, 2.011. That means this number here is going to be the negative 2.011. Again, if you did the calculation and you got the negative, then the other one should be the positive. They should be the same number. So we want to be between what two numbers? Negative 2.011 and positive 2.011 would be our two values. Then it says, based on the data, can we conclude at the 0.5 level that there is a significant linear relationship between the 1980 per capita income and the 1999? So, remember here, if the null is true, we say that is no relationship. If there is If the alternative is true, then there is a relationship. A strong linear relationship. I get it all in there. So we have to do our test value. Our test value is this number right here, 1.791. The middle section is the null. The two end sections would be the alternative. We want to figure out where that number would be. Is it in one of the ends or is it in the middle? Well, 1.791 would fall in the middle section, right? 1.791 is between these two values. Since 1.791 is between those two values, is in the middle section, this is my true statement. This one is not true then. So my true statement is that there is no linear relationship. It says, based on the data, can we conclude using the 0.5 level that there is a significant linear relationship? No. There is no relationship. We cannot conclude that there is a significant relationship. Number 9, the Cadet is a popular model of a sports utility vehicle known for its relatively high resale value. For a random sample of 28 cadets, there's our N value, which means our degrees of freedom is going to be 28 minus 2, or 26. Each bought new 2 years ago and sold used within the past month. The least squares regression equation relating the two variables mileages denoted by X and used selling price denoted by Y in dollars was Y hat equals 38.23 minus 0.53X. The standard error of slope of this regression equation was approximately 0.42. Based on this information, we're going to test the population slope, the B1 value. And again, we're going to use a 10% level of significance with a two-tailed test. Since it's a two-tailed test, we're using the equals and the not equals. So, B sub 1 either equals 0 or B sub 1 does not equal 0. This one again, since we're doing B sub 1, we just have our equation that T equals B sub 1, which is the slope of your regression equation over the SSE, or the SE B sub 1, which is the least squares regression, which will give you the standard error of the least squares regression, which is the 0.42. So the SEB1 is 0.42. The plane B1 is the slope of this line. Notice the slope of that line is a negative 0.53. So B1 is negative 0.53. So I'm going to do my calculation. I'm going to take negative 0.53. I'm going to divide it by 0.42. There's my calculation. And so when I didn't do my type of t-test. I better do my type of test. We know that we're doing the t-test. We already figured out our degrees of freedom was 26, so I better fill in that blank. T-test, degrees of freedom of 26. Value of our test statistic. Hopefully by now you've got that calculated out. Negative 0.53 divided by positive 0.42 is negative 1.262. So, again, we have to remember that we're doing a two-tailed test. If this one is negative, we either have to do 1 minus the P of T is greater than negative 1.262. All right, number 9. The Cadet is a popular model of sports utility vehicle known for its relatively high resale value. For a random sample of 28 cadets, each bought new 2 years ago, and each sold used within the past month, the least squares regression equation relating the two variable mileages denoted by X and the used selling price denoted by y in dollars was y hat equals 38.28 minus 0.53x. The standard error of slope of this linear regression line was approximately 0.42. Based on this information, test for a significant linear relationship between the two variables, doing a hypothesis test regarding the population slope B1. Assume the variable y follows a normal distribution for each value and x and that the other regression assumptions are satisfied. Using a 10% level of significance, perform a two-tailed test. So again, we're doing a two-tailed test. We know a two-tailed test, we either have equals or not equals. So the population slope B sub 1 either equals 0 or B sub 1 does not equal 0. Since we're doing the standard error of the slope, we are going to do a t-test. And if we're going to do the t-test, we need to know the degree of freedom. And so we say n, the number of cadets was 28. The degree of freedom then is n minus 2. 28 minus 2 is 26. So my degree of freedom is 26. We then use the formula here for our t value. Since we're doing the population slope, that's the easier one to do. T is equal to b sub 1, which is the slope of your equation, over SE b sub 1, which is the standard error value, which is that one right there. So looking here at my equation, I'm going to find my slope. My slope is the number in front of the x. Keep in mind I have to include the sign. So in this case, my b sub 1 value is going to be negative 0.53. My SE b sub 1 value is going to be 0.42. And so in order to find t, we're going to divide those numbers. Negative 0.53 divided by 0.42. If you go ahead and do that calculation, you will come up with negative 1.262, rounding that to 3 decimal places. So again, we have to remember that we're doing a two-tailed test, that either if this is negative, you're testing to the left, or we could make it positive and test to the right. So when I'm doing my p-value, I can either do 1 minus p of t is greater than the negative 1.262. That gives me this section over here. Or I can do p of t is greater than the positive 1.262, use the right number, positive 1.262. That would give me the number to the right. Those two numbers should be exactly the same. So I'm going to calculate those out. If I calculate those out, I am going to get 0.1091. Either way, I should get 0.1091. My p-value then, I have to do the sum of those two numbers or just multiply it by 2 since I need the percent here and the percent here. We're going to round that off to 3 decimal places, so 0.218. 21.8% is in those two sections. That's what that's saying. I've got 10% or 10.9% here, 10.9% here. I want to compare my p-value to my level of significance. I have a 21.8 level of significance. I'm comparing that to the 10% level of significance, so that's going to be greater than. If my if my p-value is greater than my level of significance, then I'm going to do what with my null hypothesis? Should I reject the null or should I accept the null? Hopefully remember from all our other hypothesis testing, if the p-value is greater, I have a higher percentage of significance, then I'm going to accept whatever the null statement is. Accept the null. This is my true statement. This one then is not true. Again, on these ones, they're going to ask you if there is a significant linear relationship. If the null is true, there's no relationship. If the alternative is true, then there is a relationship. So in this case, based on the information, can we conclude using our 10% level that there is a linear relationship? No, we cannot, because the null was true.